Today we're really in the heart of the chemistry of the carboxylic acid family. Last time, after talking in sort of generalities about their chemistry, we introduced the most reactive members of the carboxylic acid family. We introduced acid anhydrides, and we introduced acid chlorides, and we talked about their chemistry. Today we're going to focus on all of the remaining members of the family. We'll talk about some of the chemistry of carboxylic acids that we haven't seen before. We'll talk about the chemistry of esters, and we'll talk about amides and nitriles. And these are all less reactive than acid chlorides and anhydrides. So if I wanted to make some generalization, here's a generic ester structure. Here's a generic carboxylic acid structure. And what I would say is, in general, these structures are less reactive. These functional groups are less reactive to nucleophiles than acids and acid chlorides. And acid chlorides and anhydrides, let's say. And so let me maybe start with an example that shows a similar type of reactivity, but it's a much less great degree of reactivity. Let's look at the reaction of a simple ester. And I think for today, for all of our examples, I'm going to be giving very small and simple compounds just because we're going to be writing out a lot of structures. So let's take a look at the simplest typical ester, methyl acetate. And the reason I say typical ester is formates are a little different. Formic acid, although it's a carboxylic acid, is a little more reactive. But acetates and propionates and various other acids, all are kind of the same. And let's take ammonia. Now, when we were talking about nucleophiles before, we talked about species like ammonia and hydroxide as basic nucleophiles. These aren't super basic nucleophiles like Grignard reagents and hydride reagents, but they're not things that are base only in name. And ammonia is a good enough nucleophile that it will react with esters. And so we undergo a reaction to get acetamide. And the other product of the reaction is methanol. So we call this reaction an ammonolysis. Meaning a lysis, a cleavage by ammonia. We've already mentioned the term hydrolysis, cleavage by water. Now, what I really wanted to be, I've been trying to keep everything simple up here. What I really wanted to draw up here was an aminolysis. These names don't matter a whole heck of a lot. An aminolysis would be with an amine like R, with, say, a general structure of RNH2, or even a secondary amine, although they're much less reactive. So there's a primary amine. But I'll show you, since I'm trying to keep all of our drawings simple today, I'll show you an ammonolysis instead of an aminolysis. And the mechanism for this, I'm not going to write it out in gory detail because you've seen all of the principles with acid chlorides and anhydrides. The ammonia is a nucleophile. It has a lone pair of electrons on it. It can attack the carbonyl, even though the carbonyl of an ester is not nearly as electrophilic as the carbonyl of an anhydride or a chloride that has a good electron withdrawing group pulling away electron density. It can attack we expel methoxide, we transfer a proton. If you want more detail, you can see your textbook for a mechanism for this reaction. But the general gist is that the carbonyl of an ester group is sufficiently electrophilic to react with a basic nucleophile like ammonia, or later on I'll show you hydroxide. Now, for all intents and purposes, the electrophilicity of the carbonyl group of an acid is really very similar to an ester, but there's one big difference. A carboxylic acid has an acidic proton. So whereas the first thing that happens when you mix an ester with an ammonia is that the ammonia attacks the carbonyl. It's not a fast reaction. It'll occur over hours of time. This is the reaction of Windex when you clean fingerprints off of the window, because grease, the oils in your skin, are esters of glycerol. They're triesters. You've heard of triglycerides. Windex has ammonia, and that ammonia is cleaving the ester groups to break them down to smaller pieces, fatty acid amides and glycerol. So that's ammonolysis. Now, if by comparison I take acetic acid and I mix it with ammonia, you might think, well, it's going to be very similar. But acetic acid has one thing that's very different than methyl acetate. It's got an acidic proton. So if I mix acetic acid and ammonia, you get a salt. You get ammonium acetate. And for the most part, you don't get an amide. Now, I say for the most part because under the right conditions, if you heat the crud out of ammonium acetate, if you heat the crud out of acetic acid and ammonia, at high temperature, you will eventually get some acetamide out of there. This is not what I would say, a useful reaction, a reaction that synthetic chemists would typically use to make an amide, but you will get some. But the first thing that'll happen, and the thing that would happen under typical conditions, would be salt formation, not amide formation.
Can you make the alcohol group a good leaving group by protonating it?
Can you? You're getting ahead of me. Can I make the alcohol group a good leaving group by protonating it? The answer is yes, and sit tight in your seat. All right, so we already talked about the concept of pKa, and we talked about the concept of pKa specifically of the conjugate acid. We said that the pKa of the conjugate acid of ammonia or the conjugate acid of an amine was about 10 or 11. And that's a typical sort of moderately basic compound, kind of the same pKa as hydrocyanic acid. Cyanide's another species that, as you just encountered on the quiz, is a reasonably good nucleophile. Now, by contrast, if you go to something like water, then you have something that's much less basic, much less nucleophilic. The pKa of the hydronium ion of the conjugate acid of water is negative 1.7. Water is very weakly basic. It is basic, but sort of in name only. So as I mentioned in our previous discussion of esters, if I just mix an ester and water, you have no reaction. And I also mentioned that that's fortunate for you because all of the lipids in your body, all of your cell membranes are made up of esters. And so if they cleaved at 37 degrees Celsius, if they underwent hydrolysis at any appreciable rate, you'd be in trouble. Now, by similar token, and again, I'm using methyl acetate. I'll use it a lot today just because it's a nice example. And then I'll use acetic acid sort of and acetamide sort of as counterpoints. But of course, these could be any esters and any acids. So by very similar token, if I mix methanol and acetic acid, again, the carbonyl is moderately electrophilic for an ester. It's moderately electrophilic for an acid. But water and alcohols are very weak bases and very weak nucleophiles. And remember, when we're scanning over pKa's and I'm tossing out numbers like -2 or -3 for the pKa of the conjugate acid of an alcohol, or -1.7 for water, and +10, we're on a log scale. In other words, we're scanning over 12 orders of magnitude. What is that? 10 to the third is 1,000, million, billion, trillion orders of difference in basicity. A trillion orders of magnitude or a trillion times different in reactivity to a first order approximation as nucleophilicity tracks with basicity. If a reaction of ammonia and methyl acetate takes a minute, roughly, then, ballpark it, you're going to say 1 trillion minutes for the reaction of water and methyl acetate, or 1 trillion minutes for the reaction of methanol and acetic acid. Well, I don't know about you. I know for me, I don't expect to be around here 1 trillion minutes from now, so they're not going to react. All right, so no reaction. All right. So chemists love to make stuff happen. They love to make what they want to have happen. And so if you want acetic acid to react with methanol, as was alluded earlier, you do something that can protonate the carbonyl group. That's going to make the carbonyl group like 1 trillion times more electrophilic. In other words, you protonate it in the presence of a very strong acid. So I could write that if I take acetic acid and I mix it with methanol in the presence of sulfuric acid, I get methyl acetate. And I get a molecule of water. And organic chemists, as I keep repeating, are very bad at balancing equations, but it's really important to keep this in mind, because this reaction is an equilibrium. And so if I go ahead and just mix them and don't have a lot of methanol, just a little bit of methanol, I'm going to have an equilibrium in the middle. Water and methanol are, for all intents and purposes, similar. I got to have a lot of methanol, or I've got to do something to soak up the water. And sulfuric acid actually really likes water, so that's one of the ways to make it hang on to drive the reaction, is just to use more than a little pinch of sulfuric acid. Question? The H2SO4 is indeed a catalyst, and technically you don't need to use a whole mole equivalent. In practice, sulfuric acid often is used in a reasonable quantity for exactly the reason I said. Because it tends to bind to the water, it helps drive the reaction as well, but it's not consumed by the reaction. So in fact, chemists, when they write a reaction like this, will often show solvent and reagents with an arrow. And so you'll often see this written as sulfuric acid. Sometimes you'll see it written as a catalyst, with parenthesis cat. And often you'll see methanol just indicated it's the solvent. Now with acetic acid, I might use as little as possible, but if I have a valuable carboxylic acid, I'm probably going to use a whole big splash of methanol, a whole pot of methanol, a whole flask full of methanol for a couple of grams of acid. And so here's our product of the reaction. Now, this reaction's been known for a long time. It was discovered or invented by Fischer, and so it's called a Fischer esterification. Sometimes people will use sulfuric acid for the reaction. Sometimes they'll use another strong mineral acid like hydrochloric acid. Ironically, in the laboratory, if I want dry hydrochloric acid in methanol, not in water, so I don't want to go to a bottle in the laboratory in the stockroom and get HCl with water in it, one of the ways I'll do that, one of the ways I'll get anhydrous HCl and methanol is to throw some acetyl chloride into my methanol. It'll react to give HCl and methanol and methyl acetate. And those all will be just the methyl acetate I might not pay attention to, and then I might use this as a reaction to take a big valuable carboxylic acid and make a methyl ester out of it. So this is often how we roll in the laboratory. All right, let's take a look at the mechanism of the reaction. So in acid, protons go on and off all different lone pairs. Any lone pair that's weakly basic is going to get protonated. It's an equilibrium. If I throw sulfuric acid, a strong acid, into methanol, it dissociates, it protonates the methanol. So my strongest acid in methanol is protonated methanol. It's the leveling effect you learned about in general chemistry. So protons go on, protons come off. When the carbonyl gets protonated, the carbonyl goes from being moderately electrophilic to being very electrophilic. We show the flow of electrons by drawing a curved arrow from the electrons to the hydrogen, representing the formation of a new bond. Electrons flow back on to the oxygen atom. We have an equilibrium. We generate protonated acetic acid. Plus methanol. I'll put my electrons. I'm not always good about writing my lone pairs, but I'll put my lone pair of electrons back onto the oxygen where they belong. Now, this process, the protonation of the carbonyl, has made it into a good electrophile. Now it's ready to react even with a relatively weak nucleophile like methanol. Electrons flow from the lone pair on methanol to the carbonyl-carbon atom. We start to form a bond, but concurrently, because we can't have 10 electrons around the carbon, concurrently, electrons flow up on to the oxygen atom. So we get an OH group here, and we get a methoxy group with a proton and a positive charge on it, and another OH group, and I will try to be as good as I can about keeping track of all of my lone pairs of electrons. So we formed a tetrahedral intermediate. And in strong acid, protons go on, protons come off. Protons go on and off every lone pair of electrons. And so you could think of it as a proton being directly transferred among there. I probably think of this more as being mediated by solvent. I'd say that's a better way to think about the process. And so in our equilibrium, we have lots and lots of methanol around. Protons flow on, protons flow off. I will draw a curved arrow representing the flow of electrons back to the methanol. Doesn't matter which side I write the proton on, which side I write the lone pair of electrons on. I'm representing a tetrahedral oxygen atom, an oxygen atom with 4 substituents equally disposed about it. I guess you'd call it trigonal pyramidal for the geometry of the oxygen. All right, so that sort of takes us to an uncharged tetrahedral intermediate. And this looks a heck of a lot like a geminal diol if you think about it. And the common theme in all of this chemistry that we've talked about is these types of tetrahedral intermediates, these types of geminal diols, are not generally stable. The end of last lecture, at the end when we were talking about acetals, or in a previous lecture, hemiacetals, I mentioned glucose, a cyclic example that was stable. We'll see a tetrahedral intermediate that's stable in the discussion section where you actually have it as a low energy species. But in general, tetrahedral intermediates are not stable. They're not something that you can isolate or put in a bottle. They're just a high energy species, stable enough that it's in an energy well, stable enough that it can sit around for a microsecond, but not stable enough that you could put it in a bottle. And so our reaction continues. In strong acid, protons come on, protons go off. If we put a proton back on the methoxy group, we're just on the backwards pathway. And so I'm going to continue forward. Protons come on and off every lone pair of electrons. And so now we've protonated one of our OH groups. Doesn't matter which one gets protonated, they're both equivalent. Remember, we're just tetrahedral about this oxygen. Now, just as we had the attack, we can have a breakdown now with the expulsion of water. Electrons flow down from the oxygen. We can't stop at that point because that would force us to have 10 electrons around carbon. Carbon can't accommodate 10 electrons, and so we're going to break down. Actually, I am going to be a good person and write this mechanism on different lines. So give me a moment here. I'm just going to continue to balance here. And so I will write the breakdown of this tetrahedral intermediate in the next step. All right, so as I was saying, electrons flow down from the oxygen. They flow back onto the oxygen. This gives us a molecule of the protonated methyl ester. And we have expelled a molecule of water. And our final step is the very reverse of the first step of the reaction. In the first step, we put a proton onto a carbonyl. In the last step, we take a proton off of a protonated carbonyl. We're in this vast sea of methanol. Remember, this is an equilibrium reaction. If we don't have a lot of excess methanol, you're going to get only partial conversion to the ester. So we have a ton of methanol floating around. Our methanol, which in protonated form served as the catalyst, is now going to accept a proton. Our protonated methanol at the very first step of the reaction was consumed. Our acid catalyst was consumed. In the very last step, it is regenerated. And so those 6 steps constitute the mechanism for our Fischer esterification. They constitute the mechanism for ester formation. Thoughts or questions?
The acid has to protonate the CO double bond, the oxygen on top because the nucleophile is a weak nucleophile.
Which step?
Oh, sorry. The first step on the bottom of the chalkboard. Oh.
Here.
No, sorry. Yeah, on top.
So your question is, why does it protonate this oxygen? Why is this oxygen protonated?
No. Why is the CO double bond oxygen protonated? Sorry, it's on the bottom right.
Here?
Yeah.
Why is this protonated? Because when we push electrons down over here, it ends up with a positive charge on the oxygen. Now remember, in the back of your mind, when you see this structure, as we just saw in the quiz, there are multiple contributing resonance forms. So that is one resonance form. Think in your mind for a second about 2 other resonance forms. You can picture another resonance form in which the positive charge is on this carbon, and a third resonance form in which we have a double bond to this oxygen, single bond to this oxygen, and a positive charge on this oxygen. And collectively, all 3 of those resonance structures make up a picture of the actual species. Just as in your oxocarbenium ion, I asked you to draw one structure, although it was fine if you drew 2 resonance structures, or it was fine, as a matter of fact, if you draw any of the 2 resonance structures. So we're just thinking about one of the different pictures that are present, in part because if you look at this, it's already a long mechanism, and so you're sort of holding in the back of your head all of this relevant stuff. All right. Any other questions? Then I want to talk about the reverse reaction, the hydrolysis of esters. Remember, Fischer esterification is an equilibrium. So if I take, and again, I'm keeping my whole lecture really simple with simple small molecules. If I take methyl acetate and I treat it now with water and sulfuric acid, I'm going to hydrolyze it to acetic acid plus methanol. It's just the reverse of the reaction. I could write it like this. I could write it like this, saying I'm treating it with sulfuric acid in water. It's all the same thing. And since this is so identical to what we just saw, at this point, you should be able to write a mechanism for acid-catalyzed ester hydrolysis. I'll leave that to you. It's identical to the mechanism that I just wrote up, but in reverse. And you can figure that out. All right. I want to move on to a little bit of other chemistry of esters, carboxylic acids, and then talk about amides and nitriles. And again, I'll keep things kind of simple and general. Esters, as I said, are moderately electrophilic. They react with strong nucleophiles. If I treat an ester with sodium hydroxide, potassium hydroxide, for most intents and purposes, these are equivalent. In water, I get the carboxylate salt. And I get the alcohol. We call this reaction saponification. It's a reaction that mankind has been doing for hundreds of years before we had organic chemistry. It's the making of soap. When you take a fat, which is a triester of glycerol, 1,2,3-propane triol with 3 long-chain carboxylic acids esterified on, and you stir it with sodium hydroxide, that's Li, Drano. The sodium hydroxide hydrolyzes, saponifies the glycerol esters to get the sodium salts of the carboxylic acids that have greasy tails and polar head groups, and like both water and grease, which is very good for getting clean in the shower. Makes micelles. So, reaction here, same principle as we saw in the aminolysis. I kind of wanted to, when I was talking about this and thinking about where to present it, I kind of wanted to present it after we did the acid-promoted hydrolysis, but mechanistically, it's right up there with the aminolysis and aminolysis we talked about. In other words, here's our ester group. Hydroxide is a good base, a moderately strong base, a relatively strong base. It's a good enough nucleophile. It attacks our carbonyl. I'll give you a little bit of an abbreviated mechanism here, only showing relevant lone pairs. We get our tetrahedral intermediate. Our tetrahedral intermediate is going to break down. It kicks out the OR group, and again, I'm just skipping a few lone pairs here. This gives rise to the carboxylic acid plus the alkoxide. And the alkoxide is basic, and so the alkoxide reacts to form the carboxylate. And again, I'm not going to write out every curved arrow and every step in painful detail, but the carboxylate reacts to give you the alkoxide salt, and the alkoxide reacts to give you the carboxylate salt and the alcohol. And in a preparative sense, if I carry out this reaction in the laboratory, and I want to isolate my carboxylic acid, a very common laboratory procedure to saponify an ester with sodium hydroxide, then wash the aqueous layer that contains the carboxylate salt to remove the alcohol and any unreacted ester, to extract it with ether, to wash it with ether. And then very commonly in the laboratory, you will acidify with some strong acid in water like HCl or H2SO4 and isolate from there the carboxylic acid. Sometimes in the laboratory it will precipitate out. All right, so that gives us a little bit of an overview of carboxylic acids and of esters. And now I want to move on to the last members, the last main members. There are plenty of other members in the carboxylic acid family, but I want to move on to the last main members of the family, on to amides and nitriles. Amides, I'll write them in general form with two R groups here. That could be two hydrogens, in which case we have a primary amide, a hydrogen, and an R group, in which case we have a secondary amide, or two R groups, in which case we have a tertiary amide. Nitriles look very different, and yet in some ways are very similar. Both of these compounds are generally less reactive toward nucleophiles than esters. And I think it's kind of easy, at least, to compare an amide to an ester. We already saw this in the IR. The stretching frequency for the amide carbonyl is lower. There's less double bond character. The nitrogen of the amide is less electronegative than the oxygen of the ester. The nitrogen of the amide is better able to donate in electrons by resonance to the carbonyl, making it less electrophilic. And so a general principle is that amides and nitriles generally react less quickly. And so if I tried to epitomize this with a reaction, and again, I'm going to write very simple compounds, so I will write acetamide, but again, this could be any amide. If I imagine treating it with sodium hydroxide and water, like we did with our ester in saponification, how would I epitomize this? I'd say long time or heat to make it react. So let's say delta or long time would be how I describe this. And again, we get hydrolysis, we get cleavage by the sodium hydroxide to the carboxylate salt. And in this case, since we have a primary amide, to ammonia. Now, what do I mean by long time? Well, actually, Drano, which I mentioned for ester cleavage, is a good example. When hair, you get your drain clogged up with hair, is made up of protein, which are polyamides. When I throw Drano down the drain, it doesn't unclog the drain instantly. The Drano sits with the hair and the grease that are down the drain for a number of hours before it unclogs it. In the laboratory, if you want to speed this reaction along, you could boil your sodium hydroxide with an amide. But unlike my comment about trillions of seconds for the water-promoted hydrolysis of an ester, the reaction occurs even at room temperature at a reasonable rate on the laboratory time scale. And again, nitriles, maybe a hair less reactive than amides. I know that problem comes up on your sapling. But honestly, I don't think of them personally as being very different. So I can say sort of ditto if I take acetonitrile and treat it under these conditions with sodium hydroxide in water, maybe with heat or a long time, a few hours. I'll get, again, sodium acetate plus ammonia. All right, by now you should be reasonably strong in your mechanistic understanding of carboxyl compounds, and maybe I'll just give you a quick abbreviated tour of some of the mechanisms here. Your textbook has them in more detail if you want, but all of the principles that you can think about are similar. Hydroxide's a reasonably good nucleophile. It's basic, it can attack, we can kick up, form a tetrahedral intermediate. And in part here, I really don't want to lose the forest from the trees. This is the gist of this mechanism. Your textbook writes the next step in the mechanism as kicking out NH2-. I think it's okay to think about that. The realities may be a little bit more complicated. In some cases, one can see di-deprotonation occurring, but I think in terms of your thinking right now, it's fine to think about this. Anyway, so that gives us our carboxylic acid and our amide anion. The amide anion is very basic. You can think of it as pulling off a proton on the carboxylic acid to give you the carboxylate plus ammonia. And for nitriles, again, I don't want to get fantastically into a whole lot of mechanism here. And so maybe I'll just sort of start us out here on the mechanism. There's a lot of proton shuffling that's going on. But the gist, remember the theme that I talked about in carbon-nitrogen double bonds is basically in very many ways, they're like carbon-oxygen double bonds. And in a similar way, carbon-nitrogen triple bond is very much like a carbonyl or a carbon-nitrogen double bond. And so if you look at acetonitrile, you can think of it, so now we're looking at the hydrolysis of nitriles. You can think of this as being very similar. In other words, hydroxide adds, we kick in electrons. You get a negative charge on nitrogen. We're going to shuffle some protons around. I'll say minus H plus. In other words, you can think of this, or I guess first we're going to put on a proton here, so I'll say plus H plus. Of course, that's not plus H plus. That's water going ahead and protonating. You can think of this as minus H plus as the next step. Again, we've got sort of a lot of tedious proton shuffling in the mechanism at this point. And I'm abbreviating things a little bit. One thing to keep in mind, again, this theme that I mentioned where carboxylate, where nitrogen-carbon double bonds are very similar to carbon-oxygen double bonds. And so this structure here is really just like the analog of a carboxylate. In other words, there are two resonance structures here. And again, I'm kind of abbreviating this. And so we have two equivalent resonance structures. And then the last step you can think of is just that we're going to pick up a proton, and I'll draw this explicitly. It's nice to be able to pick and choose the resonance structure that you want when you're writing a mechanism. And so I'll just say our last step here is going to be protonation. In some cases, you can stop your nitrile hydrolysis at the primary amide. In other cases, the amide is going to go on further all the way to the carboxylate. All right, just as esters can be hydrolyzed by aqueous acid, amides can be hydrolyzed by aqueous acid, nitriles can be hydrolyzed by aqueous acid. If I take some amide, I'll write this as RCONR2', and I cook it up with acid H3O plus and water. Maybe heat that a little bit. And again, of course, you can't go to the stockroom and get a bottle of H3O plus. It's going to be sulfuric acid and water or HCl and water. You'll get the carboxylic acid and the corresponding ammonium salt. So if I took acetamide as just an example, since I was using acetamide in the previous panel and I talked about trying to stick to small molecules, and let's say I cooked that up with sulfuric acid and water, and maybe a little bit of heat, boiled it up. you get the ammonium salt, the ammonium in this case bisulfate HSO4 minus, and the carboxylic acid. And this is a reaction that's done in the laboratory with proteins. If you want to break down a protein into individual amino acids, for example, if you want to extract the amino acid proline from hair clippings, and this is a procedure in organic syntheses, you can take 6 molar hydrochloric acid, that's about half the strength in the bottle, boil your hair or boil your protein with it for a number of hours, and it will break down to the individual amino acids. So it's a very standard way to hydrolyze amides. And again, I've just given acetamide as an example to keep the structure small here. Do the same thing just for comparison with acetonitrile. For the sake of simplicity, I'll just write ditto marks here. And you get the exact same products. You get the corresponding acetic acid and the ammonium bisulfate salt. And maybe since all of this is really, really, really analogous to ester chemistry, all the things we covered, maybe I'll say write as an exercise on your own, write a mechanism for, let's say, the acid-promoted nitrile hydrolysis. Quick question?
Yeah, so for the blackboard on the left, can the OH group just perform a nucleophilic attack on the carbonyl?
Yes, yes, yes. And I was only starting us out on the nitrile hydrolysis. So in the cleavage of the nitrile by sodium hydroxide to the corresponding amide, yes, indeed, you first, to the carboxylic acid, the first step is the hydrolysis to the amide, and then it continues on.
Oh, okay.
So, and sometimes if you're careful, you can control it and stop it at the amide stage. All right. The last couple of minutes that I would like to take here, I want to talk about a few sort of synthetically useful reactions and kind of wrap up our carboxylic acid chemistry. So we haven't really talked about where acid chlorides come from. And basically, acid chlorides are high in energy, and so you make them from other highly reactive species. Acid chlorides, indeed, remember when I started out, I said every member of the carboxylic acid family can be interconverted by some chemistry or another. And so I'm only giving you a little bit of a smattering here. But making an acid chloride is a very useful reaction. Treating a carboxylic acid with thionyl chloride is a great way to do it. There are a few other species that are also used for this, but thionyl chloride, SOCl2, is particularly popular. And the products of the reaction are the carboxylic acid chloride, plus, if we're going to write a balanced equation, sulfur dioxide and HCl, hydrogen chloride gas, which generally bubble out. So I don't want to go into full detail on the mechanism, and again, I'll leave it to your textbook to do this, but I do want to bring out a theme that highlights this chemistry. Thionyl chloride is kind of a sulfur acid chloride. It's kind of a double acid chloride of sulfur. Indeed, this is very similar to another species, phosgene, which has a carbon here, which also does this reaction. It's a very reactive molecule. It's extremely electrophilic. You've got two chlorines pulling electron density away from sulfur. through the same types of chemistry that we saw for acid chloride reactions, carboxylic acids can react with thionyl chloride to give an intermediate that looks like a funny anhydride. And this is a theme that you should pick up on in seeing the forest from the trees in this chemistry. And that is that all of these species where you have a carbonyl with an ester linkage, where you have a carbonyl with an ester-like linkage to another electrophilic species, the carbonyl becomes super electrophilic. And nucleophiles can attack, even not very good nucleophiles can attack at there. And this theme, forget the details now, look at the theme. We've kicked out chloride already. That's one of the byproducts. Chloride can come in, form a funny-looking tetrahedral intermediate, and that intermediate can fall apart, kicking back, kicking out sulfur dioxide, so we get our acid chloride, sulfur dioxide, and chloride anion. And when you write a balanced equation, since a proton was lost at the very beginning, you get HCl. All right. That same theme reemerges in other carboxylic acid chemistry. Remember, this is the theme of the anhydride. This is the theme that when you have something electron withdrawing on the carbonyl, it makes it into a good electrophile. And so your textbook gives you another reagent, which in various forms and variations is quite popular for forming esters and amides. We will see it again in the very last lecture when we talk about the chemistry of amino acids, peptides, and that reagent is DCC. And the general idea is acid chlorides and acid anhydrides are generally species on the way to somewhere. They're generally things that you're making to use. Esters and amides are widely valuable, important compounds. They're stable enough to be in drugs. They're the proteins and peptides in your body, and they're molecules that are a lot of interest. And so being able to take a carboxylic acid and an alcohol and make an ester is an extremely valuable operation. Being able to take a carboxylic acid and an amine, I'll write it as a primary amine, although it could be a secondary amine or ammonia for that matter, and make an amide, that is an extremely valuable operation. And a reagent that often gets used for this is called DCC. There are variants of it, but what this reagent is dicyclohexyl carbodiimide. The carbodiimide functionality is another member of the carbon dioxide family of molecules, and carbonic acid and carbon dioxide are essentially like a double acid, carboxylic acid. Carbon's in the +4 oxidation state here. The carbon-nitrogen bond is electrophilic, and the carboxylic acid in the above case can add to the carbon-nitrogen bond. And here's where this theme comes in. So here's our cyclohexane ring. The CC is cyclohexyl carbodiimide, so we have a cyclohexane ring. And here's the big picture. Here's the big idea. The carbodiimide reacts in exactly the same way we see thionyl chloride. It reacts to make something that looks a heck of a lot like an anhydride, because remember, the carbon-nitrogen double bond is very similar to the carbon-oxygen double bond. And a nucleophile can come in, just as we have seen time and time again, with all of the chemistry we've been seeing today. A nucleophile can come in, and I'm just going to abbreviate CY for cyclohexane. Our nucleophile can come in, and we can kick back and kick out, and eventually basically end up giving rise to our acyl nucleophile, our acylated nucleophile above, and dicyclohexyl dicyclohexyl urea, which is a byproduct of this reaction. So DCC is a very useful reagent for making esters and amides. All right, the last thing I want to do, your textbook has nicely kind of picked and chosen a few additional key reactions. And I'd like to remind you of these, although I know that you also will be able to learn about them from the reading. And these reactions basically fit in the broad theme that we've seen. Lithium aluminum hydride is a super, super good hydride nucleophile. It can push hydride into practically any double or triple bond between carbon and any sort of electronegative atom. It can push it into a carbonyl group. It can push it into an imine. It can push it into a nitrile. Lithium aluminum hydride generally reacts completely to reduce things down. And so your textbook has chosen as a couple of examples to show you in the chemistry of nitriles that lithium aluminum hydride can react with a nitrile to give a primary amine, adding in 2 equivalents of hydride, temporarily going through an intermediate where you have aluminum on the nitrogen. Your textbook has chosen to remind you, and this is again just a smattering of the rich chemistry of the carboxylic acid family, much of which you're going to be guided not by having, and this is where people always make a mistake in learning chemistry, organic chemistry, not by memory, because there's way too much of it, but by broad principles. All the principles we've seen today, you can apply to all the members of the carboxylic acid family and basically intuit lots and lots of different reactions. So your textbook has also pointed out and reminded you that nitriles can be reduced selectively. And we saw this in esters. We said lithium aluminum hydride blasts the heck of an ester all the way down to an alcohol. Dibal is a more mild reducing agent. It can stop and only add 1 equivalent of hydride. And so your textbook chooses to give you an example of a dibal reduction of a nitrile with water as a workup, or you can use H3O plus as a workup. Remember, you're going to get an imine initially, but as was aptly asked early on, I think the gentleman in the 3rd row there, about primary imines. Primary imines generally aren't stable and break down to the corresponding aldehyde in water conditions. And I'll give you 2 more examples from your textbook while we're talking about the chemistry of nitriles. And again, I could show you many other examples. So Grignard reagents and organolithium reagents, I'll call it R prime MgX or R prime Li, followed by an aqueous workup, H2O, or H3O plus can add to give you ketones, like so. And again, this is the same general idea that we've seen before, the idea that these nucleophiles can add. In the case of the nitrile group, you often can stop at one addition, which is something you generally can't do with esters. Anyway, I think that basically wraps it up for the chapter. We will be picking up with chapter 23 next time. Thank you.